Right now, in the darkness of the room around you, something is arriving. It has been traveling since before you drew your last breath, since before you closed your eyes, since long before that, in some cases, arriving in a straight, unbroken line from somewhere far away, or from somewhere very close, like the small red glow of a charger light across the room, or the faint seep of a street lamp through the curtain. You cannot feel it land. It has no weight you could measure on your skin, no sound, no temperature you would notice, and yet it is touching your eyelids at this very moment, brushing against the closed skin the way wind brushes against a field of grass, except this visitor moves so quickly and so quietly that grass would not even have time to bend before it was already gone, already replaced by the next arrival, and the next, in a stream too fast and too fine for any of your other senses to register. This is light, and even though you have lived your entire life inside it, swum through it every waking hour, felt its warmth on your face, and watched it fall in stripes across a kitchen floor in the late afternoon, it remains, if you sit with it for even a moment, one of the strangest things in the entire universe. Tonight, we are going to sit with it. Slowly, without hurry. There is nowhere else to be, and nothing you need to solve. We are simply going to let the mystery of light unfold in your mind, the way a slow tide moves across a beach, one gentle wave at a time, until the questions themselves become as soft and rhythmic as breathing, and you drift, without noticing exactly when, into sleep. Let's start with the simplest fact, the one that sounds almost too obvious to mention, and yet contains almost everything strange that follows. Light is a form of energy. Not energy the way a battery holds energy, sitting still and waiting, but energy that is always moving, always in transit, incapable of standing still even for an instant. Physicists describe it as electromagnetic energy, which is a phrase that sounds complicated, but is really just describing two things happening together, hand in hand, like two dancers who can never let go of each other. There is an electric part and a magnetic part, and as one rises, the other rises with it, and as one falls, the other falls too, over and over, endlessly, as the whole pair races forward through space. You do not need to picture the mathematics of this to understand the feeling of it. Picture instead a small ripple moving across still water, except this ripple never needs water to move through at all. It can cross the emptiness between stars. It can cross the black vacuum of space for millions of years and arrive here, tonight, having lost none of its motion, none of its urgency, along the way. And this brings us to the first quiet mystery, the one worth turning over in your mind as your muscles loosen and your breathing slows. If light is not a solid thing, not a liquid, not even really made of the same stuff that makes up your blanket or your pillow or your own hand resting there in the dark, then what, exactly, is it made of? For a very long time, this question divided the sharpest minds in the study of nature into two quiet camps. Some believed light was made of particles, tiny bullets fired out from every candle flame and star, invisible and impossibly small, but bullets all the same, traveling in straight lines because that is simply what small solid things tend to do. This was the view favored by Isaac Newton, the same man who worked out the laws that describe how apples fall and planets orbit. Newton spent long hours in a darkened room in Cambridge, shutters closed except for a single small hole, letting one narrow beam of sunlight fall onto a glass prism, watching it fan out into a soft ribbon of color on the far wall. He believed those particles of light were simply being sorted, the way pebbles of different sizes settle into different layers when you shake a jar of sand and gravel. But other thinkers, working in the same rough era, looked at the very same evidence and arrived at an entirely different picture. They believed light was not a particle at all, but a wave, more like sound, more like the ripple spreading outward when a stone breaks the surface of a pond. A Dutch scientist named Christian Huygens, working not long after Newton, proposed that light spread outward in waves from every glowing source, each point of light producing its own tiny ripple, all of them overlapping and combining into the great advancing wavefront we actually experience. For a while, the wave idea faded into the background, mostly because Newton's reputation was so towering that few scientists wanted to argue against him directly. But roughly a century later, an English polymath named Thomas Young performed a deceptively simple experiment. He let light pass through two narrow, closely spaced slits cut into a card, and on the screen behind, instead of two simple bright lines, he found a whole pattern of stripes, bright and dark, alternating, in a way that only made sense if the light passing through each slit was behaving like a wave, spreading out and overlapping with itself, sometimes reinforcing, sometimes canceling out entirely. It was a quiet, careful piece of evidence, and it seemed, for a long while afterward, to have settled the matter in favor of waves. You might think that would be the end of the story, a single, tidy answer, safe to file away and stop wondering about. But nature, it turns out, does not always cooperate with our need for tidy answers. In the early years of the 20th century, physicists studying how light strikes certain metals found something that waves alone could not explain. When light hit these metal surfaces, it would sometimes knock tiny particles called electrons loose, but only if the light was of a certain kind, and the details of exactly which electrons came loose, and how energetically, did not match what a simple wave should produce. Albert Einstein, in 1905, the same remarkable year he also explained the wandering motion of pollen grains suspended in water and introduced his special theory of relativity, proposed something startling. Light, he suggested, actually does travel and interact in small discrete packets after all, later given the name photons, even while it also, somehow, continues to spread and interfere and behave exactly like a wave in situations such as the one Thomas Young had discovered more than a century before. Both descriptions were correct. Neither one, alone, told the whole story. This is the strange and honestly rather beautiful place where our understanding of light has rested ever since, refined over the following decades, but never resolved into one single simple picture, the way you might resolve a puzzle by finding the last missing piece. Light behaves like a wave when it is spreading, interfering, bending gently around edges. It behaves like a particle when it strikes a single electron or a single molecule at the back of your eye, delivering its energy all at once, in one complete packet, or not at all. Which behavior you observe depends, in a way that still humbles physicists today, on exactly how you choose to look. But here, in this dark room, none of the bat complexity is asking anything of you. The photons crossing the space between the street lamp outside and your closed eyelids do not care whether you think of them as waves or particles. They simply arrive, carrying their small, quiet packets of energy, the way they have arrived at every eye, human and animal, since the very first light-sensitive cell blinked open in some ancient, warm, shallow sea. And this arrival raises the deeper question we are slowly circling tonight, the one underneath all the history and the experiments and the careful men in darkened rooms with their prisms and their slits and their metal plates.
If light is simply energy crossing empty space, arriving everywhere at once, falling equally on a stone, a leaf, a closed eyelid, a mirror, a shadow, then why does anything become visible at all? Why does some of this ceaseless, invisible traffic of energy turn, somewhere between the object it strikes and the mind that perceives it, into the vivid, colored, dimensional world you see the moment you open your eyes? Long before anyone asked why light turns into vision, human beings were already living inside that mystery without a name for it. Picture one of the earliest fires, tended in the mouth of a cave, 40,000 years ago, its light throwing enormous trembling shapes across the rock wall. A person moves an arm, and a shadow, 20 times its size, leaps and folds across stone that has never moved in its life.
There is something almost unbearably strange about this if you actually stop to notice it. The way a small, solid thing can throw an enormous dark twin of itself onto a distant surface, a twin with no weight, no texture, nothing you could touch, and yet unmistakably there. Children still discover this same astonishment today, holding their hands up in a lamp's beam, delighted and faintly unsettled by the rabbit or the bird that appears on the wall, obedient to every twitch of their fingers. Our very distant ancestors had that same delight and unease. Except for them, there was no explanation waiting nearby, no textbook, no teacher who could say, simply, that a shadow is only the shape of an obstruction, the outline of wherever light has been prevented from going. For most of human history, a shadow was simply a fact of the world, taken in without being understood, the way you accept the softness of sand under bare feet without needing a theory of granular materials. Fire itself was the first great turning point, long before anyone wrote a word about optics. Once early humans could carry a flame, could feed it and shelter it, and coax it back to life from a bed of embers, they possessed something no other creature on earth had ever controlled, a source of light they could summon on command, deep in the darkest part of night, in the coldest months, in caves so far from any opening that not one particle of sunlight had ever reached that stone before. Think of what that must have meant, practically and also quietly, privately, emotionally. A world that had been carved in two, obedient to sunrise and sunset, suddenly had a crack in it. Darkness was no longer absolute, and with fire came the first mirrors, though nothing like the mirrors you might picture. Still water was the original one, of course, older than any human hand, but the first manufactured mirrors were discs of polished obsidian, that black volcanic glass, ground and buffed by hand in places like Anatolia more than 8,000 years ago, until a face could be seen faintly swimming in the dark surface. Later came bronze, tin, polished silver, each slightly better at returning an image than the last, though every one of them dimmer and more distorted than the mirrors you use without a second thought each morning. Someone, somewhere, in some quiet workshop, was the very first person to catch their own reflection this clearly, and there is no record of what they thought in that moment, only the mirror itself, buried later in a grave, as if it had been considered too strange or too precious to leave behind. Lenses came from a different kind of accident, or at least a different kind of noticing. A drop of water sitting on a leaf will bend the light passing through it, and if you have ever looked closely at such a drop, you may have noticed that whatever lies beneath it, a vein in the leaf, a grain of soil, appears magnified, swollen, closer than it should be. Ancient peoples noticed this too,
in water, in certain polished stones, in chunks of clear quartz and rock crystal. Among the Assyrian ruins of Nimrud, in what is now northern Iraq, archaeologists found a small oval piece of ground rock crystal, nearly 3,000 years old, shaped in a way that modern lens makers immediately recognized. No one is entirely certain what it was used for, whether as a magnifying glass, a fire starter, or simply a decorative inlay, and that uncertainty is worth sitting with rather than rushing past. It is entirely possible that people were bending and focusing light on purpose long before they had any language at all for what bending and focusing meant. The Greeks and Romans later understood well enough that a clear sphere of glass or polished ice, held at the right distance from dry leaves or tinder, would draw the sun's light down into a single fierce point hot enough to ignite a fire, and they used this trick deliberately, calling such objects burning glasses, without ever quite untangling how light was managing this feat.
And then there was the rainbow, which must have felt like the strangest event of all, because it asked for no tools, no fire, no polished stone, nothing but rain and sun and the right angle between them. A rainbow cannot be touched, cannot be walked toward, seems to hover in the sky, obeying no object anyone can point to, and it vanishes the moment a cloud drifts in front of the sun. It is not surprising that nearly every culture that left us a written or spoken tradition wove some story around it: a bridge for gods, a bow left hanging by a war god who had finished fighting, a promise, a warning, a path between the world of the living and whatever lay beyond it. The rainbow asked, quietly and repeatedly, across thousands of years and thousands of different peoples, the very question this whole story keeps circling back to: what is light, actually, that it can be bent into such an orderly ribbon of color, and why does it choose to show itself this way only sometimes, only briefly, only from certain places, and never others? By the time trained thinkers in ancient Greece began writing seriously about vision, they had inherited a puzzle without a single agreed answer, and they split, broadly, into two very different camps. One idea, associated with philosophers like Empedocles and later refined by Plato, held that the eye itself sent something out, a kind of visual fire or invisible ray, which traveled outward from within a person and touched the world, feeling its shape the way an outstretched hand might feel a wall in the dark. This is usually called the emission theory, and it has an intuitive appeal you can still sense if you have ever felt as though someone was staring at you from across a room before you even turned to check. The opposing idea, developed by thinkers such as Democritus and Epicurus, and later shaped further by Aristotle, proposed something closer to the reverse, that objects themselves gave off thin films or forms of themselves, and that these somehow traveled to the eye and entered it, so that seeing was a kind of receiving rather than a kind of reaching. This second family of ideas is usually called intromission. Euclid, writing around 300 BCE, worked out an elegant geometry of sight built on rays traveling in straight lines, useful for understanding perspective and shadows and reflection, but his geometry worked almost as well whether you imagined those rays leaving the eye or entering it, and so the deeper argument about direction simply continued, unresolved, for well over 1,000 years. It was not settled by pure argument, in the end. It was settled, or at least decisively reframed, by patient, careful, almost stubborn experimentation, centuries later, in the city of Cairo, by a scholar named Ibn al-Haytham, known in the West by the Latinized name al-Haytham. Around the year 1027,
Confined for a long stretch under house arrest, he devoted himself to the study of light with an intensity that reads, even now, as something close to obsession. He built darkened rooms with a single small hole in one wall, watching how the light of the world outside painted an inverted image of itself on the wall behind him, an early camera obscura, and he asked himself, with real rigor, what those observations demanded of any honest theory of vision. If the eye were sending out rays to feel the world, he reasoned, there was no good reason those rays should be blocked or distorted by pinholes and screens in the particular geometric way they clearly were. Light, he concluded, carefully and against much of the received wisdom of his time, must be traveling from the object into the eye, not the other way around, arriving in straight lines that could be traced, measured, and predicted. It was quiet, unglamorous work, done mostly alone, in rooms kept deliberately dark, so that a single beam of daylight could be studied in isolation, and it would take several more centuries, and several more curious, patient minds working in workshops and studies, scattered across Europe and the Islamic world, before that single insight fully reshaped how anyone understood the humble, mysterious act of simply opening your eyes. Even after al-Haytham had settled the question of direction, even after it was clear that light traveled from the sun and the candle and the glowing coal into the eye rather than the other way around, a deeper question remained, patiently waiting its turn. What, exactly, was doing the traveling? If light moved through space in straight lines, the way an arrow moves, then what was the arrow made of? For a long time, nobody had a satisfying answer, and it would take almost 8 more centuries, and a shift in the kind of question being asked entirely, before one began to emerge. Strangely, the answer did not come from anyone staring hard at light itself. It came from people who were, on the surface, studying something else altogether, the quiet, prickling behavior of magnets and electric currents. In the early 1800s, in London, a bookbinder's apprentice, with almost no formal schooling, began attending public science lectures in his spare time, taking careful notes, and eventually talked his way into a job washing bottles in a laboratory. His name was Michael Faraday, and he would go on to become one of the most gifted experimentalists in the history of science, entirely self-taught in mathematics, working instead through touch and observation, and an almost childlike willingness to ask simple questions.
Faraday noticed that a magnet, just sitting on a table, seemed to organize the space around it. Sprinkle iron filings on a sheet of paper held above a magnet, and they arranged themselves into smooth, curving lines, arcing from one end of the magnet to the other, as if something invisible were reaching out into the room and gently combing the space into shape. Faraday called these lines of force, and he came to believe they were not just a convenient way of drawing a picture. He believed the space itself, around a magnet or a charged object, was genuinely altered, filled with an invisible condition he called a field, whether or not any iron filings happened to be there to reveal it. It fell to a younger physicist, a Scotsman named James Clerk Maxwell, working a few decades later, to take Faraday's rough, hand-drawn intuition and translate it into the precise language of mathematics. Maxwell was, by most accounts, a rather unusual and quietly playful mind, the kind of person who as a child reportedly asked his mother endless questions about the causes behind everything, want to know, he called it, in his own childhood dialect, and that want to know never really left him. Working through the 1860s, Maxwell managed to write down a small set of equations describing how electric fields and magnetic fields behave and how they relate to one another, and buried inside that mathematics
almost as an unplanned bonus, was something remarkable. The equations predicted that a changing electric field would create a changing magnetic field nearby, which would in turn create a changing electric field a little further out, each one regenerating the other, in a kind of self-sustaining relay racing outward through space. This was, mathematically, a wave. And when Maxwell calculated the speed at which this electromagnetic wave ought to travel, using nothing but numbers gathered from laboratory experiments on electricity and magnetism that had nothing obviously to do with light, the answer that fell out of the equations matched the known speed of light almost exactly.
Maxwell himself seems to have found this startling. He wrote that the agreement between the numbers seemed to show, hardly avoidably, that light itself was an electromagnetic disturbance propagating through the field, according to the very same laws that governed magnets and electric currents. Light was not some separate mystery substance. It was electricity and magnetism, chasing each other outward, together. Now, it is worth pausing gently here, because this is exactly the point where an old and very natural misunderstanding likes to creep in, and it is worth setting aside carefully, the way you might set aside a stone before lying down. When people hear the word wave, they tend to picture a wave in water, or a wave moving through a rope shaken at one end, and both of those pictures share something important. There is a physical substance doing the waving. Water rises and falls. Rope fibers move up and down. For a long stretch after Maxwell, many physicists assumed something similar had to be true of light, that there must be some invisible substance filling all of space, a medium they called the luminiferous ether, through which electromagnetic waves rippled the way ripples move through a pond. It was, in its way, a very reasonable guess, and enormous care went into trying to detect this ether, to measure the world's motion through it. But the careful experiments kept coming back empty. There was no ether to find, and the picture that eventually replaced it, stranger and yet in some ways simpler, is that the electric and magnetic fields do not need a substance to ripple through at all. The field is not a stuff, in the way water is a stuff. It is better thought of as a condition, a set of values, existing at every point in space, values which can rise and fall, strengthen and weaken, in a rhythm that spreads outward on its own, without needing anything material to carry it. If you want a gentler, closer analogy, think of the wave that ripples around a packed stadium when spectators stand up and sit down in sequence. The wave clearly travels, all the way around the bowl, visibly moving, but no single spectator travels with it. Each person simply stands and sits, in place, and it is the pattern, the timing, that moves. Electromagnetic waves are a little like that, a traveling pattern of change, though even this comparison should be held loosely, the way you might hold a warm cup rather than grip it, since ultimately the field is its own kind of thing, not quite reducible to anything more familiar. Once light is understood this way, as a traveling rhythm of electric and magnetic change, several familiar words start to make a more concrete kind of sense. Picture the wave stretched out in space, rising and falling in a smooth, repeating pattern, the way a very long, gentle piece of ribbon might be laid down in soft loops. The distance from the top of one loop to the top of the next is called the wavelength, and it can be almost anything, from the size of a mountain range down to something smaller than the nucleus of an atom. How often a full loop passes a given point in 1 second is called the frequency, and the two are bound tightly together. A shorter wavelength always means a higher frequency, more loops crowding past in the same second,
the way shorter, choppier waves lap against a dock faster than long, slow ocean swells. The height of each loop, how far the field swings above and below its resting value, is called the amplitude, and this is the quality that corresponds most closely to what you would experience as brightness or intensity. A taller wave carrying more energy through the same space, the way a bigger wave at the shore carries more force than a ripple. And frequency itself turns out to be tied to energy as well, in a separate but related way, so that higher frequency light, however faint or bright, carries more energy in each of its smallest possible parcels than lower frequency light does, a detail that will matter more later, when the story turns toward the strange, grainy, almost reluctant way light sometimes behaves.
All of this, wavelength, frequency, amplitude, describes a single, vast, continuous family, stretching far beyond anything the eye can register. At one end sit radio waves, with wavelengths that can span the length of a football field or more, gentle, low-frequency ripples used to carry music and voices across whole countries. Moving toward shorter wavelengths, you pass through microwaves, then infrared light, the warm, invisible glow radiating quietly off skin and stone, and the sun-warmed hood of a car. Only after all of that, tucked into an almost absurdly narrow band, comes the small sliver of wavelengths the human eye happens to be built to catch, what people simply call visible light. Beyond it, wavelengths keep shrinking into ultraviolet, then X-rays, capable of passing through soft tissue, and finally, gamma rays, with wavelengths smaller than a single atom, carrying enough energy to rearrange matter itself. The whole spectrum, from the longest radio wave to the shortest gamma ray, is, underneath it all, the very same thing that Maxwell wrote into his equations, the very same rhythm of electric and magnetic field that reaches your eye each evening as ordinary daylight, fading now, gently, into the particular narrow band of it your own eyes were built, slowly, over a very long stretch of evolutionary time, to notice. There is one more property of this rhythm worth settling into before the story moves on, and it is perhaps the strangest of all, though it took the better part of a century for anyone to notice how strange it really was. Light, moving through empty space, always travels at the same speed, no matter who is doing the measuring or how fast they themselves happen to be moving. This sounds like a small, technical detail, the kind of thing that belongs in a footnote, but it is not. It is one of the few facts about the universe that refuses to bend to common sense, and once you actually sit with it, turn it over slowly, in a quiet room, it starts to feel less like a fact about light and more like a fact about the very fabric that light moves through. Think for a moment about how speeds normally add together. If you are walking down the aisle of a moving train at a gentle pace, and someone standing still on the platform outside watches you go by, your speed, relative to them, is your walking speed plus the speed of the train itself. This is so obvious, so built into the way bodies move through the ordinary world, that it barely counts as a discovery. It simply matches what anyone would expect from tossing a ball while running, or watching a boat cut across a river with a current pushing it sideways. Velocities stack. They add. Nothing about that has ever felt strange, because nothing about it has ever needed to. But light does not do this. If you could somehow ride inside a rocket moving at half the speed of light and switch on a flashlight pointed straight ahead, you would not measure the light leaving that flashlight at 1.5 times its usual speed.
even though intuition, trained entirely on trains and rivers and thrown baseballs, insists that you should. You would measure it moving away from you, at exactly the same speed light always moves, the same number that anyone standing still back on Earth would also measure, watching your rocket and its light from far away. Two observers, moving relative to each other at a tremendous difference in speed, look at the very same beam of light and arrive, independently, at the very same number. This was not a guess. It was measured. The first serious hint of this came in the late 19th century, from a set of experiments performed by Albert Michelson and Edward Morley in a basement laboratory in Cleveland, using an instrument sensitive enough to detect the faintest of speed differences. At the time, physicists believed that light, like sound waves in air or ripples across a pond, needed some medium to travel through, an invisible substance called the ether, thought to fill all of space. If the Earth was plowing through this ether as it moved along its orbit, then light, measured in the direction of that motion, should travel slightly differently than light measured against it, the same way sound frequencies shift, as a train's whistle changes pitch when it moves toward you and then away, or the way it takes longer to swim against a current than with one. Michelson and Morley built their instrument with exactly this expectation in mind, confident it would detect the drift. It did not. No matter which direction they pointed their apparatus, no matter what time of year they measured, when the Earth's own motion through supposed space should have been pointing a different way, the speed of light came back exactly the same. It was one of the most famous null results in the history of science, an experiment that succeeded precisely by failing to find the thing it was looking for. It took another 2 decades, and a young patent clerk in Switzerland, with a gift for imagining what things would look like from someone else's vantage point, to work out what this result actually meant. Albert Einstein, in 1905, simply took the strange finding at face value. He did not try to explain it away, or search for some overlooked flaw in the measurement. Instead, he asked a quieter, more radical question. What if the speed of light really is the same for every observer, always, under all circumstances, and everything else has to bend around that fact instead? It turned out that if you accept this single premise, and follow its logic all the way through without flinching, something has to give elsewhere. Because if speed is distance divided by time, and the distance and the relative motion between two observers can differ, and yet the speed always comes out the same, then time and distance themselves cannot be the fixed, universal backdrop everyone had always assumed them to be. This is the part that tends to keep people awake the first time they really absorb it, though tonight is exactly the wrong time for that kind of restlessness. So let it settle instead, as something gently fascinating, rather than alarming. Two observers moving at different speeds relative to each other will genuinely disagree about how much time has passed between two events, and about how far apart those events were in space. Neither of them is wrong. There is no hidden true answer that one of them simply failed to measure correctly. A clock moving very fast relative to you will tick, from your point of view, more slowly than an identical clock sitting beside you, and this is not an illusion caused by signals taking time to travel, the way a lightning flash reaches your eyes after the strike itself. It is a real difference in how much time elapses, confirmed again and again with fast-moving particles in accelerators and with atomic clocks flown on airplanes. Clocks that land having ticked forward by a few billionths of a second less than their twins that stayed on the ground.
Space itself stretches or compresses depending on how fast you are moving relative to what you are measuring. The only thing that stays fixed, the only anchor in this otherwise fluid arrangement, is the speed of light itself. Everything else,
distance, duration, even the very notion of two events happening at the same moment, turns out to be something the universe is willing to negotiate, depending on where you are standing and how fast you are moving while you watch. It is worth pausing here, because there is a common and very understandable confusion that tends to creep in once people learn that light always travels at this one fixed speed, and it involves what happens when light passes through water, or glass, or the lens of an eye. Light slows down in these materials, famously, which is the entire reason a straw in a glass of water looks bent, and the reason a lens can bring a scattered image into focus. It is tempting, hearing this, to imagine that light itself is somehow interrupted along the way, ricocheting from atom to atom inside the glass, pausing at each one, like a traveler ducking into shops along a street, and then hurrying to catch up. But that picture, appealing as it is not quite right. Between the atoms of any transparent material, in whatever open space exists there, light still moves at its one true, unchanging speed. What happens instead is subtler, and has to do with the way light's oscillating fields interact with the charged particles inside the material, nudging them, being nudged back, so that the overall wave that emerges on the other side behaves as though it has been delayed, its net progress through the material slowed even while its true, instantaneous speed between interactions never wavers.
The bending itself, the visible kink in the straw, the reason a lens can gather a spray of light into a single sharp point, comes directly out of this slowing, out of the fact that light moving at an angle into a denser material has one edge of its wavefront held back before the other, swiveling the whole beam the way a marching line of people pivots when one end of the row steps into mud while the other still strides across dry ground. It is a beautiful piece of behavior, and it deserves its own unhurried look, because it turns out to explain a great deal more than just crooked straws and reading glasses. But that is a story for later, because the mention of a lens bending light brings up something else worth wandering into now, something that starts, as it happens, with exactly this kind of bending. In the late 1660s, a young and rather solitary Isaac Newton, working in a room at Cambridge with the shutters closed and a single hole cut to let in a narrow shaft of daylight, placed a glass prism in that beam and watched it spread the white sunlight into a ribbon of colors on the wall behind it. This was not, on its own, a new observation. People had seen rainbows in prisms and in raindrops for as long as there had been prisms and raindrops. What was new was Newton's insistence on treating the colored band not as some trick performed by the glass, some contamination the glass was adding to pure white light, but as something the white light already contained, hidden in plain sight, waiting to be sorted out. He tested this with a second prism, arranged to catch the spread-out colors and recombine them, and watched the ribbon collapse back into a plain white spot, and then, in a further and even more telling experiment, he isolated a single color from the first ribbon and passed it through a second prism alone, and found it bent again, but did not spread any further, did not fracture into other colors the way the original beam had. Red stayed red, blue stayed blue. Whatever the prism was doing, it was not painting the light. It was sorting a mixture that had been there all along, the way a sieve does not create different sizes of gravel, but merely separates sizes that were already jumbled together. What Newton had stumbled onto, though he did not yet have the language for it, was the fact that what we experience as the color of light corresponds to something physical, to the wavelength of the electromagnetic wave doing the traveling. Longer waves, when they reach a human eye and are registered there, tend to be seen as red, shorter ones as violet, and in between,
lies the whole familiar procession: orange sliding into yellow, yellow into green, green into blue, that Newton's second prism could never further divide, because each color already represented, for the light in question, a single distinct wavelength, and a single wavelength has nothing left within it to be sorted. This is worth sitting with for a moment, because it means that in a very real sense, color as a physical property is simple and continuous, a smooth gradient of wavelength running from the longest visible red down to the shortest visible violet, with no boundaries, no natural divisions, nothing in the physics itself that says where red ends and orange begins. Any such boundary is drawn later, and it is drawn not by the light, but by something looking at the light. That something, in your case, is a retina, lined with two broad kinds of light-sensing cells, rods and cones. The rods extraordinarily sensitive but colorblind, doing most of their work in dim light, and contributing nothing to your sense of hue. And the cones, far less sensitive but far more discerning, coming in three varieties, each tuned by a slightly different pigment to respond most strongly to a different stretch of that wavelength gradient, one favoring the longer, reddish end, one favoring the middle, greenish stretch, and one favoring the short, bluish end. It was Thomas Young, another Cambridge scholar working around a century after Newton, who first proposed on largely theoretical grounds that three such receptor types would be enough to explain human color vision, an idea later refined by Hermann von Helmholtz in Germany into what is still called the Young-Helmholtz trichromatic theory, and confirmed physiologically only much later, once instruments existed sensitive enough to measure the absorption of individual cone pigments. The key insight, and it is a genuinely strange one once you let it settle, is that no single cone type on its own tells your brain anything at all about wavelength. A given cone simply responds more or less strongly depending on how much light of the wavelengths it favors happens to be present, and it cannot distinguish a dim light at its favorite wavelength from a brighter light at a wavelength it merely tolerates.
Color, as your nervous system constructs it, is not read directly off the light, the way a barcode scanner reads a barcode. It is inferred, computed, assembled from the comparative firing rates of three cone types working in concert, the way you might guess the exact shade of a paint from the mixed reports of three friends with different degrees of color blindness, none of whom alone could tell you the shade, but whose combined testimony narrows it down. This inference does not stop at the retina. The signals from the three cone types are almost immediately recombined, further downstream, into a different and rather more efficient coding scheme, one Ewald Hering proposed in the 19th century, arguing against Helmholtz at the time, though the two views turned out eventually to be compatible rather than contradictory, each describing a different stage of the same process. In this opponent scheme, the raw cone signals are converted into three new channels, one comparing reddish signals against greenish ones, one comparing bluish signals against yellowish ones, and one simply tracking overall brightness, light against dark. This is why, if you stare at a bright red shape for a long moment, and then look at a blank white wall, you tend to see a ghostly green afterimage where the red shape had been. The red-green channel, having been pushed hard in one direction, rebounds in the other once the stimulus is removed, like a spring released after being held compressed. It is also why you have likely never seen, and cannot really picture, a reddish-green or a yellowish-blue, the way you can easily picture a yellowish-green or a bluish-red, since those pairs sit at opposite ends of a single opponent channel and are built, at the level of your nervous system, to cancel one another out, rather than combine. All of this machinery is also the reason that mixing colors of light behaves so differently from mixing colors of paint, a distinction that trips up almost everyone at some point, usually in childhood, usually while finger painting. When you mix light, you are adding wavelengths together, stimulating more cone types more strongly, and the result moves toward white, which is why the red, green, and blue lights on a screen, overlapped in the right proportions, produce white, and why this is called additive mixing. When you mix paint, you are doing something closer to the opposite. A patch of red paint looks red not because it is emitting red light, but because it is being struck by ordinary white daylight, which contains every visible wavelength, and the paint is absorbing most of those wavelengths and reflecting mainly the longer, reddish ones back to your eye. A blue paint is likewise absorbing most wavelengths and reflecting mainly short, bluish ones. Mix the two paints together, and each pigment continues absorbing what it always absorbed, so the combination reflects only the narrow band of wavelengths that neither pigment has removed, which is why mixed paints tend to grow darker and murkier rather than brighter, a process fittingly called subtractive mixing, since each added color subtracts more of the available light rather than adding to it. And because color is something your visual system infers from three comparative signals rather than something it reads directly off a spectrum, wildly different combinations of wavelengths can produce cone responses so similar that they are, to you, visually indistinguishable, a phenomenon called metamerism, which is the entire reason a shirt that matched your trousers perfectly under the fluorescent light of a shop can look subtly, maddeningly mismatched once you step outside into daylight, the two fabrics reflecting different mixtures of wavelengths that only happen to fool your three cone types into agreement under one particular lighting condition. This same inferential looseness is also, strangely, the reason magenta exists at all as something you can see and name, even though there is no such thing as a wavelength of magenta light, no place on Newton's spread ribbon where it appears. It arises only when your longer and shorter cones are both strongly stimulated at once while the middle ones are comparatively quiet, a combination that never occurs from a single pure wavelength, but occurs easily when red and violet light, from opposite ends of the visible spectrum, arrive together, and your visual system, faced with no direct spectral answer, closes the gap by inventing one, bending the straight line of the spectrum back around into a circle, and filling in, right where red and violet ought to meet, a color that exists nowhere in the light itself, but only in the accounting done afterward, in the dark, behind your eyes. Let that thought settle for a moment, this strange fact that a color you can plainly see corresponds to no wavelength at all, and let your attention drift toward something plainer, something you can almost feel rather than merely think about. What happens, physically, when a beam of light simply meets a surface? Because before there was color theory, before there were cones and opponent channels, there was just this: light traveling in a straight line through empty space or through air, and then arriving at some boundary, some edge, where one material ends and another begins, and having to decide, in its blind physical way, what to do next. Some of that light bounces back. We call this reflection, and it is happening constantly, everywhere, at every surface you have ever looked at, which is, in fact, the only reason you can see most things at all, since very few objects around you produce their own light. The page of a book, the skin of an apple, the wall beside your bed, none of these are glowing. They are simply reflecting, redirecting some portion of whatever light happens to be striking them back out into the room and into your eyes. A mirror is not special because it reflects light, and other things don't. Nearly everything reflects light. A mirror is special because it reflects it so uniformly, so smoothly, that the reflected rays preserve the exact geometric arrangement they arrived in, rather than scattering off in 1,000 directions the way light does when it strikes something rough, like paper, or skin, or plaster. That scattering is called diffuse reflection, and it is why you cannot see your face in a wooden tabletop no matter how clean it is, while a still pond, glassy and undisturbed, will show you your face perfectly, because water, when it is calm, behaves almost like a mirror at its surface. Some of the light that meets a surface does not bounce away at all. It is absorbed, taken in, its energy converted into the faint jostling of atoms that we register, if the surface is being struck by enough of it, as warmth. This is why a black stone, left in the sun, grows hot to the touch, while a pale one nearby stays cool, the dark stone absorbing nearly the whole visible spectrum, instead of sending most of it back out as reflected light. Absorption and reflection are, in a sense, the light's two simplest choices at a boundary: bounce or be swallowed. But there is a third option, one that only becomes available when the second material happens to be transparent, or at least partly so, and that third option is refraction, which is really just a fancy word for bending. Refraction happens because light travels at different speeds in different materials. In a vacuum it moves at its true, maximum speed, but in air, it is slowed by a hair, and in water, it is slowed rather more, and in glass more still, and in diamond, more than almost anything else you're likely to encounter. This slowing, on its own, wouldn't cause any bending if the light arrived at the boundary head-on, perfectly perpendicular to it. But if it arrives at an angle, one edge of the beam enters the slower material and begins lagging just an instant before the rest of it does, and that tiny difference in timing across the width of the beam is enough to swing its whole direction, the way a marching line of people will pivot if the person on one end steps into deep mud while the other end is still crossing dry ground. This is the reason a straw in a glass of water looks broken at the surface, why a spoon appears to bend the moment it dips below the waterline, and why swimmers, reaching for something on the bottom of a pool, routinely misjudge its position, because the light carrying that image to their eyes has already been quietly bent on its way up through the water and into the air. People noticed this bending long before they understood why it happened. The scholar, Ibn al-Haytham, working in Cairo around the year 1000, studied refraction carefully enough to measure it, though the precise mathematical rule connecting the angles wouldn't be pinned down until centuries later by the Dutch astronomer Willebrord Snell in the early 1600s, a relationship now generally called Snell's law, even though there is some evidence the Persian scientist Ibn Sal had already worked out something close to it 600 years earlier, and simply left no lasting record loud enough to be remembered for it. Refraction, once you notice it, explains a great deal that otherwise seems mysterious. Take a glass prism, that solid wedge of triangular glass that seems, at first glance, like little more than a curious paperweight. Shine ordinary white sunlight into one face of it, and a full, ordered rainbow spills out the other side, violet through red, in the same fixed sequence every time. This happens because glass doesn't slow every wavelength of light by quite the same amount. It bends violet light a little more sharply than red light, since shorter wavelengths interact more strongly with the electrons in the glass. So a beam of white light, entering the prism as a single tidy ray, exits as a fan,
each color peeling off at its own slightly different angle, a phenomenon called dispersion. Isaac Newton demonstrated this with a prism in his rooms at Cambridge in the 1660s, and then, in a stroke that settled a debate people had been having for a very long time, took a second prism and used it to bend that fanned-out rainbow back together into plain white light again, proving that the color hadn't been added by the glass at all. It had been hiding inside the white light the entire time, and the prism had simply sorted it out, the way shaking a drawer of mixed coins might sort them by size as they settle. That same trick of dispersion, performed not by glass but by countless floating raindrops, is what produces an actual rainbow in the sky, sunlight entering each droplet, bending, reflecting once off the droplet's curved inner back wall, and bending again on its way back out, with red light emerging at a very slightly different angle than violet, so that across a whole field of raindrops, each one sending its own narrow sliver of the spectrum toward your eye, the full arc appears. And dispersion, or something closely related to it, is also responsible for the shimmering false pool of water that seems to lie on a hot road on a summer afternoon, a mirage, in which the air near the scorching asphalt is much hotter and thinner than the air above it, bending light from the sky upward into your eyes at a steep angle, so that you appear to be looking at a reflective puddle when you are in truth looking at nothing but heated air behaving briefly like a mirror. Refraction can also trap light entirely, under the right circumstances, in something called total internal reflection. If light traveling inside a dense material like glass or water strikes the boundary at a steep enough angle, it cannot escape into the thinner material beyond at all. Instead of bending out, it reflects entirely back inward, as if the boundary had become a mirror. This is the principle, quietly, behind a diamond's sparkle, since diamond bends light so strongly that rays entering it bounce internally several times before finding an angle shallow enough to exit, scattering out as flashes, rather than escaping cleanly, the way they would from a plainer stone. It is also the principle behind fiber optic cables, in which light is sent bouncing down a hair-thin strand of glass for miles, trapped by this same total internal reflection at every point along its curving path, carrying, in the end, almost everything that now travels across the internet. And bending light on purpose, rather than simply observing where it happens to bend, is precisely what a lens does, a carefully shaped piece of curved glass or curved liquid that refracts every incoming ray by just the right, carefully calculated amount, so that rays which started out scattered from a single point on some object all converge again to a single point on the far side, reassembling, faithfully, a small and often upside-down image of the world, which is, quietly, exactly what is happening right now behind your own closed eyes, in the soft curved lens sitting just behind your pupil, bending the last, gentlest light of the evening into a picture on the inner wall of your eye before you drift, finally, past the need to make any picture at all. But before that final picture fades, it's worth lingering a little longer on the light itself, and on a behavior it has that is stranger, in some ways, than anything about lenses or mirages or diamonds.
Because so far we have mostly been treating light as though it travels in straight, simple lines, rays, bouncing and bending, but always tracing a clean path from one point to another. And for most ordinary purposes, that picture works perfectly well. But light, it turns out, is also a wave, and waves do something rays alone never could. They interfere with each other. Think of two stones dropped into a still pond a little distance apart. Each one sends out its own set of ripples, spreading outward in perfect circles. Where those ripples cross, something interesting happens. If a crest from one ripple arrives at the exact same place and moment as a crest from the other, the two add together, and the water rises higher there than either ripple alone would have made it. But if a crest from one arrives where a trough from the other happens to be, the two cancel out, and the water, just for that instant, goes still, as though neither stone had ever been dropped at all. This is interference, and it is one of the clearest signatures that something is behaving as a wave rather than as a simple stream of particles. Particles, ordinary ones, don't do this. Two marbles thrown across a room don't cancel each other out when their paths cross. Waves do. Light does this too, and a scientist named Thomas Young showed it beautifully in the year 1801 in a room in England, using nothing more exotic than a candle, a card with two narrow slits cut into it, and a screen. He let light pass through the two slits and land on the screen beyond, and what appeared there was not two bright patches, as you might expect if light traveled only in straight rays from each slit. Instead, there was a whole series of alternating bright and dark bands, stripe after stripe, fading gradually toward the edges. The bright stripes were where light waves from the two slits arrived in step with each other, crest meeting crest, adding up into extra brightness. The dark stripes were where they arrived out of step, crest meeting trough, canceling into darkness. Young had shown, quietly and with very simple equipment, that light interferes with itself, which meant that light, whatever else it might be, was unmistakably behaving as a wave. It was a controversial claim at the time, since the towering authority of Isaac Newton had leaned toward thinking of light as a stream of small particles, and many of Young's contemporaries were reluctant to set that picture aside. But the stripes on the screen were difficult to argue with. For interference to appear cleanly like this, the two waves being compared need to keep a steady, predictable relationship to each other as time passes, what physicists call coherence. A candle flame, or a light bulb, or the sun doesn't produce this on its own, because the countless individual atoms inside are each emitting their own little bursts of light at their own moments, with no coordination between them, so the pattern of crests and troughs is constantly, randomly shifting. That's why Young had to be clever, sending light from a single narrow slit onward to the two slits, so that whatever randomness was in the original light source got imposed identically on both paths, keeping them synchronized with each other, even if not with anything else. A laser, invented in the 20th century, solves this problem far more elegantly, since it produces light in which vast numbers of atoms emit in near-perfect step with one another from the very start, all crests and troughs aligned, which is part of why laser light shows interference and diffraction effects so vividly and why it can be focused down to such a fine, precise point. Diffraction is a close cousin of interference, and it shows up whenever a wave encounters an edge, a slit, or a small obstacle. You've likely noticed something like it if you've ever watched water waves in a harbor spread out into a fan shape after passing through a narrow gap in a breakwater, curving into the calm water behind it rather than continuing on as a straight beam. Light does the same thing, just on a much smaller scale, because its wavelengths are so tiny, a few hundred nanometers, a distance you could fit many thousands of times across the width of a human hair. Shine light through a narrow enough slit, or past a sufficiently fine edge, and instead of casting a crisp-edged shadow, it will spread out and produce its own soft pattern of light and dark fringes at the boundary, the wave bending gently around the obstacle rather than ignoring it. This is why a very small aperture in a camera, or in your own eye, doesn't simply produce a sharper and sharper image forever as it narrows. Past a certain point, diffraction starts working against you, blurring the image because the light itself refuses to travel in a perfectly straight, unspread line through such a tiny opening. There is another wave property worth mentioning gently here, since it explains something you have probably already used without thinking much about it. Polarization. Light waves oscillate as they travel, vibrating side to side in a direction perpendicular to the direction they're moving, the way a plucked guitar string vibrates up and down along its length rather than moving forward. But unlike a guitar string, which vibrates in one fixed plane, ordinary light contains waves oscillating in every possible direction at once, up and down, side to side, and every angle between. A polarizing filter, like the lenses in a good pair of sunglasses, is built with a microscopic structure that only allows light vibrating along one particular direction to pass through, blocking the rest. That's why polarized sunglasses are so good at cutting glare off water or pavement. Sunlight reflecting off a flat horizontal surface becomes partly polarized in the horizontal direction as it bounces, and a filter tuned to block exactly that direction can dim the glare substantially while letting through plenty of the more randomly oriented light coming from everything else you're trying to see. All of this, interference, diffraction, polarization, depends on light having a phase, meaning a specific position within its own repeating cycle of crest and trough at any given moment. The same way, a point on a rotating wheel has a specific position within its rotation. Phase is what allows two waves to be described as in step or out of step with each other in the first place, and everything about interference comes down to comparing phases and seeing whether they align or clash. Here is where the story becomes genuinely strange, though, and worth sitting with slowly rather than rushing past. If you dim the light going into a double-slit experiment far enough, down to a level where individual photons are arriving one at a time, each one striking the screen and registering as a single tiny point, with long gaps between arrivals, you might expect the interference pattern to disappear, since interference seems to require two waves overlapping, and a lone photon has nothing to overlap with. But that isn't what happens. Each single photon still lands as one dot, unmistakably particle-like in that instant. Yet if you leave the experiment running for long enough, letting thousands upon thousands of these individual, isolated photons accumulate one dot at a time, the dots slowly assemble themselves into exactly the same striped interference pattern Young saw with his candle, bright bands and dark bands, built up speck by speck, like sand collecting into dunes. Somehow each individual photon behaves, statistically, as though it had explored both slits at once and interfered with itself, even though it arrived utterly alone. It is one of the most carefully confirmed and still genuinely puzzling results in all of physics, and it is a good thing to let settle quietly in the mind rather than resolve too quickly, since it points toward a deeper question about what light truly is beneath these two familiar words, wave and particle, that we've been leaning on to describe it. So let's go back, gently, to where the word photon even came from, because it wasn't handed down all at once as a finished idea. It arrived in pieces, over about 25 years, through the work of people who were mostly trying to solve much smaller, more practical puzzles than the nature of light itself. The first piece came from a German physicist named Max Planck in the year 1900, and it came out of a problem that sounds almost administrative in its dullness:
figuring out the correct mathematical formula for the glow given off by a heated object. Physicists called this glow black-body radiation, and every equation they tried to describe it with worked fine at some wavelengths and then went catastrophically wrong at others, predicting that a warm object should radiate infinite energy at very short wavelengths, which obviously wasn't happening to anyone's stove or fireplace. Planck found a formula that fit the data perfectly, but only if he assumed something odd along the way, something that even he seems to have treated, at first, as a mathematical convenience rather than a claim about reality. He assumed that the energy being radiated couldn't be given off in just any amount, smoothly and continuously, the way you might pour water from a pitcher. It had to be given off in discrete little packets, each one a fixed multiple of some very small unit. He called this unit a quantum, from the Latin word for how much, and the formula worked beautifully. But Planck himself resisted, for years, the idea that light itself was actually made of these packets.
He treated it as a strange bookkeeping trick that happened to make the math come out right, a bit like a librarian who invents an odd cataloging rule that solves a shelving problem without believing the rule reflects anything true about the books themselves. It was Albert Einstein, 5 years later, in 1905, who took Planck's bookkeeping trick and asked a much bolder question. What if the packets are real? What if light itself, not just the process of emitting or absorbing it, actually comes in these discrete units? Einstein was 26 that year, working as a patent clerk in Bern, examining other people's inventions during the day, and rewriting physics in his spare hours, and this was one of 4 remarkable papers he published in those months. The particular puzzle he turned his attention to was the photoelectric effect, which had already been observed by other physicists but never properly explained. If you shine light on certain metal surfaces, electrons can be knocked loose from the metal and fly off, and this by itself isn't surprising if you think of light as a wave, since a wave carries energy, and enough energy could plausibly jostle an electron free. But the details of the experiment refused to behave the way wave theory predicted, and the mismatch was specific enough to be genuinely troubling. If light were simply a wave, then a very bright, very intense beam should deliver more energy to the electrons, giving them more speed as they left the metal, while a dim beam should still eventually shake an electron loose, given enough time to accumulate energy, the way a gentle, repeated push can eventually get a swing moving, even if a single push wouldn't. But that isn't what experimenters found. Turning up the brightness of the light produced more electrons flying off, but it didn't make each individual electron move any faster. What determined the speed of the ejected electrons was the color of the light, meaning its frequency, not its brightness at all. And below a certain frequency, a specific threshold that depended on the metal, no electrons came off whatsoever, no matter how bright or how long you shone the light. You could leave a dim violet light on a piece of metal for a fraction of a second and knock electrons loose instantly, while a blindingly bright red light, shown for hours, would produce nothing at all. That's simply not how a wave delivering energy gradually should behave. Einstein's explanation was that light doesn't arrive at the metal as a smooth, continuous wave delivering its energy little by little, but as individual packets, each carrying an amount of energy set entirely by its frequency, following the relationship Planck had already written down in his black-body formula.
A single packet either has enough energy to knock a single electron loose in one clean interaction, or it doesn't have enough, and no accumulation of many too weak packets can substitute for it, in the same way that no number of pebbles thrown gently at a locked door will accomplish what a single well-aimed brick would. Brighter light simply means more of these packets arriving per second, so more electrons get struck loose, but the punch delivered by each individual packet depends only on its frequency, which is why violet light, with its higher frequency, can do things dim red light cannot, regardless of how much red light you throw at the problem.
It took nearly 2 more decades before this idea was fully accepted by the wider physics community, and it took until 1926 for the physical chemist Gilbert Lewis to give these packets the name we still use today, photon. Now, here is where it becomes important to slow down and separate two different kinds of claim, because they get blended together so often that the distinction quietly disappears. One kind of claim is a description of what experiments actually show, repeated and confirmed countless times across a full century since Einstein's paper. Light delivers and absorbs energy in discrete amounts tied to its frequency. Individual detectors register individual, indivisible clicks, never half a click. Dim light, spread thin enough, arrives as a sparse trickle of individual events rather than a continuous wash. These are not interpretations. They are about as close to settled experimental fact as physics gets, verified by instruments in laboratories on every continent, using methods far more precise than anything available to Einstein or Planck. The other kind of claim is different and more delicate. What does it actually mean to say that something is a photon? Is it a tiny, localized particle that simply happens to also carry wave-like information about phase and frequency along with it, like a courier who happens to also be humming a specific tune? Is it, instead, something more like a spread-out wave of probability, a mathematical description that tells you only the likelihood of detecting something at a given point, with the click itself being real, but the particle existing only in the moment of measurement, and nothing quite like a particle beforehand? Physicists still don't fully agree, and it's worth being honest about that, rather than smoothing it over. What almost all physicists do agree on is the mathematics, a theory called quantum electrodynamics, which predicts the outcomes of these experiments with staggering, almost unsettling precision, matching measurements to somewhere around 10 decimal places in certain calculations, an accuracy sometimes compared to measuring the distance between New York and Los Angeles down to the width of a human hair. But the mathematics tells you how to calculate probabilities correctly. It doesn't, by itself, settle what is actually happening to a photon between the moment it leaves a source and the moment it's detected, whether it has a definite path at all during that interval, or a definite identity as a small object traveling through space, or something else that our everyday words for wave and particle were simply never built to describe, since both of those words were invented by people watching water ripple and pebbles fly, long before anyone suspected that light might need a category of its own entirely. So when a physicist says that light is a wave, or is a particle, or offers the now familiar shrug of calling it both at once, it's worth hearing that not as a settled conclusion being handed to you, but as a kind of best available shorthand, a translation into everyday language of something the mathematics can describe far more precisely than any sentence can. And it's this very tension between behaving like a wave under some conditions and like a particle under others,
never quite both in the same measurement, that eventually pulled physicists toward asking an even stranger question, not just what light is, but what the act of measuring it might actually be doing to it in the first place. But let's set aside that stranger question for a moment, because there's a gentler and more concrete story waiting, one that doesn't require settling what light fundamentally is in order to be understood, and it starts with something almost cozy. The question of why a candle flame is orange, why a streetlight is that particular sickly yellow-pink, why a neon sign glows the specific red it glows, and why, if you could somehow look closely enough at any of these things, you'd find that the color isn't a choice so much as a signature, something closer to a fingerprint than a decoration.
Every atom, it turns out, has a kind of internal architecture for holding electrons, and that architecture isn't smooth or flexible the way a ramp is smooth and flexible. It's stepped, like a staircase, with the electrons only ever allowed to sit on particular steps, and nowhere in between. This was one of the genuinely strange discoveries of the early 20th century, and it came as a real shock to physicists who had assumed, reasonably enough, that energy ought to work the way most things in the everyday world work, continuously, in a smooth, unbroken slide from one amount to another. Instead, an electron bound to an atom can only occupy specific, separated energy levels, rather like a person on a staircase who can stand on the third step or the fourth step, but never anywhere in between, never at 3.5. If that electron is going to move from a lower step to a higher one, it needs to absorb exactly the right amount of energy to make that particular jump. No more and no less, the way you couldn't climb from the third step to the fourth by making a small hop of half a step. And when it falls back down, from a higher step to a lower one, it releases that same precise difference in energy again, this time in the form of light. Because energy and color are tied together, with each color of light corresponding to a specific packet of energy, this staircase arrangement means that atoms don't emit light in some vague general glow. They emit and absorb only very particular colors, the exact ones that match the exact gaps between their allowed steps. Hydrogen, the simplest atom there is, just one electron circling one proton, has a staircase all its own, and if you heat hydrogen gas until it glows, and then pass that glow through a prism or a diffraction grating, you don't get a smooth rainbow smeared evenly across all colors. You get a small number of sharp, isolated bright lines, a thin red line here, a blue-green one there, a violet one further along, set against total darkness everywhere else. These are called spectral lines, and they are, in the most literal sense, a portrait of that staircase, a direct visible record of exactly which energy jumps hydrogen's one electron is capable of making. Every element has its own staircase, its own unique spacing of steps, and so every element has its own unique pattern of spectral lines, as distinctive as a barcode, no two elements sharing quite the same arrangement. Sodium glows with a pair of tight, close-together yellow lines, which is why old sodium vapor streetlights bathe a road in that particular flat yellow-orange that makes everything underneath look strangely colorless, almost like a black-and-white photograph, because sodium light contains so little of any color but that one narrow yellow that there's barely any other wavelength around to bounce off a red car or a blue jacket and show you its true hue. Neon, when a current runs through it in a glass tube, produces that familiar warm red-orange glow of old shop signs, again for the same underlying reason, a staircase of energy steps that happens to correspond to red light. An argon glows a pale lavender blue. Each gas, excited by heat or electricity, tells you what it is simply by the color it chooses to emit,
and it cannot choose otherwise, because the choice was built into the atom itself long before anyone lit the tube. This is worth sitting with for a moment, in the quiet way that a small, solid fact deserves to be sat with, because it turns color from a decoration into a kind of language. A flame isn't just pretty. A candle burns orange partly because of tiny glowing particles of soot, heated hot enough to glow across a broad range of colors all at once, which is a different phenomenon we'll return to in a moment. But if you toss a pinch of table salt into that same flame, you'll see it flare briefly into an intense yellow, the unmistakable signature of sodium atoms in the salt being kicked up their staircase by the heat, and then tumbling back down, releasing that same yellow line hydrogen and sodium streetlights share. Copper burns green. Strontium burns a deep red. This is, quite literally, the chemistry behind fireworks, where different metal salts are packed into shells, specifically because chemists long ago learned which element produces which burst of color: strontium for red, barium for green, copper for blue, without any of them needing to understand quantum mechanics to notice the pattern. Incandescence, the glow of that candle's soot, or a wood fire, or an old-fashioned incandescent light bulb's glowing filament, works differently, and it's worth telling apart from these sharp spectral lines. When something is heated hot enough, its atoms and molecules jostle around with so much energy that they emit light across a broad continuous range of colors all mixed together, rather than a few clean isolated lines, and the mixture shifts as the temperature rises, from a dull red glow at lower heat, up through orange and yellow, toward a white-hot blaze at higher temperatures still, and if you could push it further, toward blue.
This is why a blacksmith,
Without any thermometer at all, could read the temperature of a piece of iron just by its color: dull cherry red meaning one temperature, bright orange yellow meaning another, a skill passed down for centuries by people who never needed the underlying physics to use it accurately. A star works on a similar principle at an enormous scale. Its overall color, whether a cool reddish star or a blazing blue-white one, telling you roughly how hot its surface is, information astronomers still lean on today. Fluorescence sits somewhere in between, in its own strange and lovely category. Certain materials can absorb light of one color, usually invisible ultraviolet light, and then, rather than simply reflecting or scattering it, briefly hold on to that absorbed energy and release it again a moment later as a different, visible color, one that's always a bit lower in energy than what came in, since some energy is lost along the way as gentle heat inside the material.
This is why certain minerals glow eerie greens and oranges
Under an ultraviolet lamp in a dark room, why some laundry detergents contain fluorescent whiteners that make white shirts look almost supernaturally bright under sunlight or black light, catching invisible ultraviolet and converting some of it into visible blue light that our eyes register as extra brightness. And it's why highlighter pens seem to almost glow on the page, absorbing ordinary light and re-emitting a portion of it more intensely in one narrow, eye-catching color. Modern technology has learned to build the staircase deliberately, rather than simply discovering it in nature. A light-emitting diode, an LED, is built from carefully engineered layers of material, chosen specifically so that when electrons cross a particular junction inside it and drop down in energy, they release that exact energy as light of a chosen color: red, or blue, or green. The whole device essentially a tiny, human-designed staircase, built atom by atom in a factory, rather than found already existing in a star or a candle flame. A laser takes this a step further still, coaxing enormous numbers of atoms to fall down the very same step at nearly the very same instant, so that all the released light waves march out together in near perfect step with one another, producing a beam that stays narrow and pure over long distances in a way that firelight or a light bulb never could. And this brings us gently to one of the more remarkable uses humans have found for all of this staircase business. Because if every element's pattern of spectral lines is as distinctive as a fingerprint, then a beam of starlight arriving at a telescope after traveling for years, or centuries, or far longer, is itself carrying a kind of fingerprint left behind by whatever it passed through or came from. That fingerprint idea turns out to matter most when the light in question has been traveling for a truly long time, because light, for all its speed, is not instantaneous. It moves fast enough that in ordinary life we never notice the delay, fast enough that a beam from a lamp across the room seems to arrive the same instant the switch is flipped, but out among the stars that speed, however enormous, becomes almost leisurely, against the vastness of the distances involved. Light travels a bit under 6 trillion miles in a year, a span astronomers simply call a light year, not a measure of time, but a measure of distance, the distance light itself covers while a year passes on Earth. And once you have a unit like that, you start to realize something quietly strange about looking up at night. You are never quite seeing the universe as it is. You are seeing it as it was.
The nearest star beyond our own sun, a faint red dwarf called Proxima Centauri, sits a bit over 4 light-years away, which means the glow reaching a telescope tonight left that star's surface a little more than 4 years ago, back when today's date was still someone's future. It's a small delay, cosmically speaking, barely noticeable against the numbers that come next. The light from the Andromeda Galaxy, that faint smudge some people can just make out with the naked eye on a clear, dark night if they know exactly where to look, has been traveling for about 2.5 million years to reach us, which means the pattern of stars you'd be looking at is a portrait of Andromeda as it existed long before anything resembling a human being walked the earth. Some of the individual stars that made up that portrait may have already changed dramatically since then, swelled into red giants, or quietly faded, and there would be no way to know because the only version of Andromeda available to us is the old one, the one already sealed into the light on its way here. Looking outward, it turns out, is inseparable from looking backward. The deeper into space a telescope peers, the further back in time it is necessarily seeing, not as a metaphor, but as a plain physical fact of how long light takes to cross empty space. This delay becomes almost dizzying at the scale of galaxies rather than individual stars. Some of the faintest smudges captured by our most sensitive telescopes are light that has been traveling for over 13 billion years, meaning it left its source when the universe itself was still young, its structure barely settled, long before the sun or the earth had condensed out of the swirling material that would eventually become our solar system. In a very real sense, an astronomer studying one of these ancient smudges isn't just studying a distant place. They're studying a distant time, using light as a kind of frozen record, a message that has been quietly in transit since long before there was anyone waiting to receive it. Along the way, on such an enormous journey, light doesn't necessarily travel in a perfectly straight line either. Gravity, it turns out, bends the space that light travels through, and light, having no choice but to follow the shape of the space around it, bends along with it. This was one of the boldest predictions Albert Einstein made in his early 20th century work on gravity,
the idea that a sufficiently massive object, like a star or a whole galaxy, would visibly warp the path of starlight passing near it, and it was tested in 1919 when astronomers led by Arthur Eddington traveled to the island of Principe off the coast of West Africa, specifically to observe a total solar eclipse. During the brief minutes when the moon blotted out the sun's usual blinding glare, they were able to photograph stars that appeared, ever so slightly, near the sun's darkened edge, and to measure whether their positions had shifted from where they should have been, shifted by exactly the amount Einstein's equations predicted, as if their light had bent gently around the sun's gravity to reach the camera. It had. And it was one of those quiet, thrilling confirmations that reorganizes how an entire field understands the universe, because it meant gravity wasn't simply a pull between objects, but something closer to a curve in the fabric that light itself has to travel through, a landscape with hills and valleys shaped by mass, guiding beams of light the way a marble rolling across a warped tabletop is guided by the table's own contours rather than by any invisible string.
Sometimes this bending is dramatic enough to act almost like a lens, an enormous cluster of galaxies bending and focusing the light of something even more distant behind it, smearing that background light into faint arcs, or even splitting a single distant object into multiple visible images, all because the light took several different curved paths around the same massive foreground obstacle on its way to us. Astronomers now use this effect deliberately, treating certain galaxy clusters as natural telescopes, gravitational lenses assembled by nothing more than the ordinary pull of mass, magnifying and revealing objects that would otherwise be too faint and too far to ever detect. Distance changes light in a subtler way too, one connected to that fingerprint of spectral lines mentioned a moment ago. When something bright is rushing away from an observer, the light waves it emits get gently stretched out behind it, the way the pitch of a passing ambulance siren drops as it speeds away, each sound wave emitted just a little further from the observer than the last, stretching the whole sound to a lower note. Light behaves in an analogous way, though what changes isn't pitch, but color, the whole spectrum shifting toward the red end as the wavelengths stretch, an effect astronomers simply call redshift. And when the astronomer Edwin Hubble, working through the 1920s with the largest telescope of his day, methodically measured this shift in the light of galaxy after galaxy, comparing their spectral fingerprints against the known fingerprints of familiar elements measured in a laboratory, he found something remarkable. Nearly all of them were shifted toward red, and the more distant a galaxy appeared to be, the more strongly its light was shifted. The unavoidable conclusion was that the galaxies weren't just scattered through space, they were, on average, all moving away from us and from each other, the space between them steadily stretching, evidence that the universe itself is expanding. Run that expansion backward far enough, and it points toward a very hot, very dense, very early universe, one that has since cooled and thinned as it stretched outward over billions of years. And remarkably, the faint afterglow of that early heat is still detectable today, arriving from every direction at once, a nearly uniform hiss of extremely low-energy radiation, now called the cosmic microwave background. It was discovered, somewhat by accident, in 1965 by two radio astronomers, Arno Penzias and Robert Wilson, who kept finding a persistent, unexplained static in their sensitive antenna in New Jersey. Static, they at first suspected, was caused by pigeon droppings inside the instrument, only to eventually realize they were listening to the faint, cooled remnant of the universe's own early glow, stretched by billions of years of expansion into wavelengths far beyond what human eyes could ever see. Follow that light back far enough in every direction, and eventually you arrive at a kind of edge, not a wall or a boundary in the ordinary sense, but a horizon, the furthest distance from which light has had time to reach us at all since the universe began, a genuine limit on how far back and how far outward it is even possible to look. It's a strange kind of comfort, in its way, to trace light so far outward and so far backward, and then find your way home again, back down through the scale of galaxies and stars, to the small, warm, human business of seeing and building and getting through an ordinary day. Because everything we've followed out into the cosmos is, underneath it all, the same phenomenon quietly at work on your kitchen counter and in your pocket and behind your own eyes right now. Start with the eye itself, since it's the oldest light-catching device any of us own, older than any camera, refined over hundreds of millions of years of evolution rather than centuries of engineering. Light enters through the cornea, bends as it passes through the lens, and lands on the retina at the back of the eye, where two kinds of cells wait to receive it. Rods, densely packed and extremely sensitive, respond to even a handful of photons and give you your night vision, though only in shades of gray, since they can't distinguish one wavelength from another. Cones do the color work, but they need more light to fire, which is part of why a moonlit garden looks silvery and flat rather than richly colored. Your cones simply aren't getting enough to work with, and your rods, doing their best, can't tell you anything about hue at all. Each cone contains a pigment tuned to respond most strongly to a particular range of wavelengths, roughly short, medium, and long, and it's the pattern of signals across all three types, compared moment to moment, that your brain reads out as the experience of color. The color isn't sitting out there in the light itself, waiting to be found. It's a comparison your nervous system performs in real time using three overlapping instruments tucked into the back of your eye. The camera arrived much later, and for a long time it was really just an attempt to freeze what the eye already did effortlessly. The earliest ancestor was the camera obscura, known since antiquity, a darkened room or box with a small hole in one wall, through which light from outside would project an upside-down image onto the opposite surface, something painters used for centuries to trace scenes accurately before anyone had figured out how to make the image stay. That problem, of permanence, wasn't solved until the 1820s, when the French inventor Joseph Nicephore Niepce coated a pewter plate with a light-sensitive bitumen and left it exposed to a view from his window for what seems to have been several hours, perhaps even days, producing what's generally regarded as the oldest surviving photograph, a hazy, grainy image of rooftops and sky that nonetheless proved the principle. Light itself could leave a permanent trace on a prepared surface. His collaborator, Louis Daguerre, later refined the process into something practical enough to sell, and photography as an industry was born. A modern digital camera does something conceptually similar, but electronically, replacing the chemical plate with a grid of tiny light sensors, each one converting incoming photons into an electrical signal proportional to how much light struck it, the same photoelectric conversion
that puzzled physicists at the turn of the 20th century, now happening by the millions inside a device that fits in your palm. Getting information from one place to another using light turns out to be remarkably efficient, and nowhere is that more dramatically true than in fiber optic cables, the hair-thin strands of exceptionally pure glass that now carry the overwhelming majority of the world's internet traffic beneath oceans and across continents. The underlying trick is a phenomenon called total internal reflection, light traveling inside glass. When it strikes the boundary with the surrounding material at a shallow enough angle, doesn't escape at all. It bounces cleanly back inward, again and again, essentially trapped inside the fiber and guided along its length, no matter how much the cable curves and winds. Early versions of this idea existed for decades, but they were impractical for long-distance communication because ordinary glass absorbed too much light over any significant distance. A signal would fade to nothing after just a few dozen meters. The breakthrough came in the 1960s when the physicist Charles Kao, working in England, calculated that the losses weren't some unavoidable property of glass itself, but were caused by impurities that could, in principle, be engineered out. He was largely dismissed at first, but researchers at Corning Glass Works in New York took the idea seriously, and by 1970 had produced fiber pure enough to carry usable signals over a kilometer, a discovery that eventually earned Kao a share of the Nobel Prize decades later in 2009.
Today's undersea cables push pulses of laser light through glass so transparent that if seawater were half as clear, you could see clean to the bottom of the deepest ocean trench, and those pulses carry your voice, your messages, and this very story, decoded from patterns of light into patterns of sound. Light doesn't just carry information, though. It can also be converted directly into usable energy, and the effect responsible for that was first noticed far earlier than most people realize by the French physicist Edmond Becquerel in 1839, when he was only 19 years old, experimenting with electrodes in a conducting liquid and noticing that shining light on them produced a small electric current. It took well over a century of refinement before that curiosity became a practical solar cell, but the basic principle never changed. Photons striking certain materials, typically treated silicon, knock electrons loose and set them moving in a particular direction, generating a flow of electricity directly from light with no moving parts, no burning of fuel, nothing but photons arriving and electrons responding. Life discovered an even older version of this same trick, long before Becquerel, or silicon, or any human observer existed to marvel at it. Inside the chloroplasts of green plants, a molecule called chlorophyll absorbs light, particularly in the red and blue portions of the visible spectrum, which is exactly why plants look green to us, since green is the light chlorophyll reflects away rather than uses. That absorbed light energy drives a sequence of chemical reactions that split water molecules, release oxygen as a byproduct, and ultimately stitch together carbon dioxide from the air into sugar, a process so fundamental that nearly every calorie of energy in nearly every meal you've ever eaten arrived by way of a plant, at some point, catching sunlight and doing this same quiet chemistry. And light, in yet another guise, keeps time. Quartz crystals vibrate at an extremely precise frequency when a small electric current passes through them, which is how most ordinary clocks and watches keep their steady beat. But the true reference standard for time itself, the definition the whole world quietly agrees to, comes from atoms and light together. Inside a cesium atomic clock, electrons are coaxed to jump between two very specific energy levels, absorbing and releasing light at a frequency so mathematically constant that it's used to define the second itself, precisely 992,631,770 oscillations of that particular transition, a number chosen deliberately to match the traditional length of a second as closely as science allows. Every phone that adjusts its own clock automatically, every GPS satellite calculating your position from tiny differences in signal timing, is quietly relying on this same atomic light-based rhythm running somewhere far away, mostly unnoticed. It's worth pausing, gently, on the difference between these three things that light does for us, because they're easy to blur together: illumination, which simply lets you see what's around you; information, which is light shaped into a pattern that can be decoded, like a photograph or a fiber optic pulse; and energy, which is light doing physical work, releasing electrons, splitting water molecules, warming a hand held near a window. The same beam of sunlight falling on a windowsill is, at once, letting you see the room, and warming the wood beneath it, and, if a small leaf happens to be resting there, quietly being turned into sugar. One kind of light, three entirely different jobs, all happening at once, without any of them getting in each other's way. And yet, for everything light does, there remains a question sitting quietly underneath all of it, one that has never been fully settled, no matter how many decades physicists have spent circling it. It's the question of what actually happens in the moment of measurement. Earlier, this narration described how a photon, before it's observed, behaves as though it's spread across every possible path, a wave of probability rather than a single definite thing, and how the instant something detects it, a screen, an eye, a photographic plate, that spread collapses into one specific outcome, one flash, one photon striking one exact point. The mathematics describing this is remarkably precise. Physicists can predict, with extraordinary accuracy, the odds of a photon landing here rather than there. What the mathematics does not explain, not fully, not in any way that satisfies everyone who has looked closely at it, is why the collapse happens at all, or what, exactly, counts as a measurement in the first place. A camera counts, a human eye counts, but does a single stray air molecule bumping into a photon count too? Does the collapse happen at one sharp instant, or is it something gentler and more gradual, a slow leaking away of possibility that only looks sudden from the outside? Different physicists, across the 20th century and into this one, have offered different answers, and those answers do not agree with each other, not because anyone lacks the mathematical skill to work out the details, but because the question sits at a place where physics brushes up against philosophy, where the equations run out and interpretation has to begin. There is, for instance, the idea that the wave doesn't collapse at all, that instead, the universe quietly splits, every time a measurement occurs, into separate branches, one where the photon landed here, another, equally real, where it landed there, all of them continuing on forever, unaware of each other. There is the idea that there's a hidden layer beneath the visible one, unseen variables, that we're always going to produce this particular outcome, even though nothing in the visible world lets us find them. There is the idea that probability itself is the deepest layer there is, that nature simply doesn't deal in certainties at the smallest scales, and asking why
is a bit like asking why a coin, once it's already landed, had to land the way it did. None of these ideas has been ruled out by experiment. That's worth sitting with for a moment, because it's rare, in physics, for a genuine disagreement to persist this long, this cleanly, with brilliant people on every side of it, and no clear way, so far, to force a decision between them. It isn't that the experiments are too crude. Some of the relevant experiments are exquisitely sensitive, capable of detecting single photons, single atoms, single quantum events. It's that the different interpretations tend to make the very same predictions about what any experiment will show, which means the disagreement lives at a level the experiments, as currently designed, simply cannot reach. It helps here to draw a careful line between two kinds of not knowing, because they feel similar from the inside, but they are not the same thing at all. There's the ordinary kind of ignorance, the kind where a question has a definite answer, and humanity just hasn't found it yet. The way, 3 centuries ago, nobody knew what caused the tides to rise and fall in the particular rhythm they do, until someone worked out the pull of the moon carefully enough to show it. That kind of ignorance is temporary by nature. It closes, eventually, given enough careful looking. And then, there's a second kind, harder to name, which isn't about lacking information, so much as lacking the right frame to even ask the question properly.
When physicists wonder what a photon is doing, between the moment it leaves a star and the moment it strikes a retina, whether it has a path, a location, a story, in any sense a person would recognize, they aren't missing a fact. They may be running up against the limits of language, borrowed from a world of marbles and waves in water, applied to something that was never built to obey either set of rules. Calling this a mystery, rather than a gap in current knowledge, isn't giving up on it. It's a way of being honest about the difference between a locked door with a key somewhere out there waiting to be found, and a door that may not open the way doors are expected to open at all. The electromagnetic field itself carries its own version of this same open question, quieter, less often discussed, but no less real. Across this narration, light has been described as a disturbance in a field, an invisible structure filling all of space, capable of rippling outward the moment a charge moves. That description works. It predicts, with stunning precision, how light bends, how it interferes, how radio waves carry a voice across an ocean. But ask what the field actually is, in the way you might ask what water is, or what wood is, and the answers grow thinner. Is it a real thing, a genuine substance occupying space, the way physicists once imagined the luminiferous ether to be, before that idea was carefully and thoroughly dismantled? Or is it better understood as a kind of bookkeeping, a mathematical convenience that lets equations balance, without corresponding to anything a person could point to and say, there, that's it, that's the field itself? Most working physicists don't spend much time worrying about this while they're doing the day-to-day work of the field, calculating orbits, or designing antennas, because the mathematics performs beautifully, regardless of which way you lean philosophically. But late at night, so to speak, when the calculating is done, the question is still sitting there, unanswered, patient, the same way it was sitting there when Faraday first sketched lines of force around a magnet, unsure himself whether he was describing something real or something merely useful. None of this should feel unsettling, particularly not now, particularly not here, in the quiet dark of wherever you happen to be resting. If anything, it might be a comfort, the knowledge that even the people who have spent entire careers staring at light, measuring it, bending it, catching it one particle at a time in darkened laboratories,
still don't have every answer. Understanding doesn't require finishing. Some of the best scientific minds in history have been perfectly at peace working for decades inside a question that never fully resolves, treating the not knowing itself as part of the shape of the work, rather than a failure of it. There's something almost restful in that, actually, once you sit with it long enough. Not every mystery is a problem waiting to be solved. Some of them are simply part of the furniture of the world, worth noticing, worth wondering about, and also worth letting go of, gently, for tonight. And so, wherever you are right now, light is still doing exactly what it has done all along, all around you, mostly invisibly. If there's any light left in the room at all, even the faint red glow of a charging cable, even the barely there gray seeping in around a curtain, it's still arriving the way it always has, as photons, uncountable in number, striking whatever surfaces happen to be in their path. Some of them reaching your closed eyes, most of them simply being absorbed by the walls, the floor, the blankets, turned quietly into a small and entirely unnoticed amount of warmth. And if the room is fully dark, that's light too, in its own way, an absence built from the same physics as the presence, the photons simply elsewhere for now, out past the curtains, caught in street lamps, still traveling in starlight from suns that finished shining long before there was anyone here to notice. Either way, nothing is required of you. No looking, no waiting, no figuring out. The universe will keep doing this same quiet work, field rippling into field, whether you're awake to consider it or not. Rest well.